All right, here's a kind of interesting example. It says, given the formula d equals at squared, where d is in meters, t is in seconds, and a is an acceleration that is in meters per second squared. That might seem like a weird combination of units there, especially if you haven't taken physics before, but it's one we're going to get used to later on. It is the correct units for acceleration in SI base units. But does the fact that the units are the same on both sides of the equation guarantee it to be correct? Well, let's look at that really quickly here. So we're saying the equation we're looking at is d is equal to a t squared. So if I want to look at that in terms of units, and maybe, some textbooks have this really formal kind of notation, and it's kind of abbreviated from what I did earlier, so I might do something abbreviated here. Maybe I won't do the full formal thing because I've seen some really formal stuff with a lot of exponents, and that gets kind of annoying. But I'm just going to use a letter L here to represent the length for d. Okay, so I'm basically I'm doing the unit, maybe I don't know if I'm translating is the right word, but I'm doing the analysis in terms of units. I'm looking at each of these quantities, and I'm replacing it by the units I think it represents. And in that sense, if acceleration A, now in the problem statement, I was actually given specific units, but I'm representing it here with dimensions, really. So meters per second squared would be like length per time squared. So I'm using capital letters for those dimensions. Like I said, this is common in some textbooks to do something like what I'm doing right here. There's a lot of different ways you can approach this, actually. And then we're seeing, okay, t squared is in the formula. So obviously t is in seconds, so that's a unit or a dimension of time, I should say. I think I said before I do screw that up once in a while. I'm going to put some parentheses here, though, maybe just to make it clear that what's inside there is what came from this variable. This square is really what was applied to that. I kind of like to do that to make it clear. It's optional, really. Somebody else doing this, if you said like, hey, so are we doing unit analysis or dimension analysis? I guess I did a dimensions type of analysis. But if somebody else said, you know what, I'm going to do it with units, and they said, I'm going to do meters is equal to meters per second squared, which is pretty clear because that's what was given, times seconds, which in turn was squared, you could do that too, and you really get to the same result. So whether you're representing your dimensions or your units, or if you do all this in your head, that's fine too. Some people will do that. The thing to notice, though, in both cases is that the time part cancels here, right? In the units case, that means the second units are going to let me make sure to get that exponent out there. So really, I've got either length is length, meters is meters. So clearly, as claimed, this formula is good on units, right? So it says, does the fact that units are the same on both sides? So yeah, units are the same on both sides, but does that guarantee it to be correct? So something to notice is like, I haven't really answered the question with what I did here. All I did was confirm something that was already given to me. So I got to think a little bit here, because like, what could possibly make it not correct? Well, as an example here, what if somebody else said, I think the correct equation to describe whatever it is that this might be describing, instead of being d is equal to at squared, somebody else comes along and says, I think it should be d is equal to 1/2 at squared. And if the first person says, well, wait, but the units work, this had to be correct, I couldn't possibly be wrong, because look, the units or the dimensions, they all work just fine. But the second person would say, yeah, but that works fine here too, because multiplying by a half doesn't change any of this. It's still going to be length is equal to a length over time squared times a time squared, or meters per second squared times a second squared. That 1/2 doesn't change that at all. What if it were like a pi instead? Turns out actually this d equals 1/2 at squared is going to be a correct formula. I don't necessarily want to say that d equals at squared is never a correct formula, because many physics formulas are kind of contextual. Like when you do problems, sometimes formulas come up in the problem. They're kind of derived based on the problem situation, and maybe there is some exotic situation where d equals at squared would turn out to be correct, but we're going to see quite a few situations where d equals 1/2 at squared is actually correct. And I don't know if we'll ever actually see this one be correct unless it's something really exotic, but it definitely illustrates the fact that one of the pitfalls of using unit balancing to try to say, okay, this must be right because the units all work, well, there could be still some numbers that don't carry units that you missed that could still have an error in them. So in that sense, it's a really cool tool to have unit balancing to check for mistakes. Physicists use it a lot. I've used it a lot. I've noticed in like math classes, people don't use this as much, and sometimes I use it to catch my own like algebra mistakes. So it's a really cool tool that you can apply in a lot of places, but just recognize it's not completely infallible.